Ever wondered how machines handle uncertainty? Like when a self-driving car guesses whether a pedestrian is about to cross the street, or when a medical AI tries to predict a patient's risk of disease. Behind these decisions are complex tools that model relationships between variables, tools like Vine copulas. But here's the thing. Traditional methods for using Vine copulas have been like using a slide rule in a world of supercomputers. They're powerful but slow, and they don't play nice with modern AI workflows. So what's a Vine copula anyway? Think of it as a flexible puzzle. Instead of forcing all variables to follow the same rules, Vine copulas let each pair of variables have their own unique relationship. This makes them great for modeling real-world data, which is often messy and unpredictable. But here's the catch. Fitting these models and using them to make predictions has always been computationally heavy. It's like trying to solve a Rubik's Cube while juggling, possible but not efficient. Enter the Vine computational graph, our solution to this problem. Imagine a roadmap that maps out every step of the calculation, like a highway system for data. This graph, or VCG, breaks down the complex dependencies of Vine copulas into a structure that's easy for computers to process. By turning Vine copulas into a directed acyclic graph, a fancy term for a flowchart with no loops, we can leverage the power of GPUs to speed things up. Here's where it gets really cool. The VCG isn't just about speed, it's about flexibility. Traditional methods forced you to follow a rigid order when sampling data, like reading a book from front to back. But our new algorithms let you choose the most efficient path, like taking shortcuts on a map. We've also made it easier to customize the model for specific variables, like focusing on certain factors in a medical diagnosis. All of this is made possible by our open-source library, torchvinecopulib. Built on PyTorch, it's like giving Vine copulas a turbo boost. And the results? When we tested it against other methods, like Monte Carlo dropout or Bayesian neural networks, our approach was faster, more accurate, and better at calibrating uncertainty. It's like upgrading from a bicycle to a rocket ship for probabilistic modeling. So why does this matter? Well, as AI systems become more complex, the need for reliable uncertainty quantification is critical. Whether it's autonomous vehicles, climate models, or personalized medicine, understanding how confident a model is in its predictions can mean the difference between success and failure. By bridging classical statistics with modern deep learning, we're not just improving tools, we're opening the door to smarter, more trustworthy AI. Imagine you're trying to predict the weather. It's not just about temperature or rain. It's about how wind patterns, humidity, and even solar radiation all interact. Traditional methods might struggle to capture these tangled connections. That's where Vine copulas come in. Think of them as a network of relationships, like a vine growing through a garden, with each branch representing how two variables connect. But this isn't just any vine. It's a high-dimensional web that can handle dozens or even hundreds of variables at once. But here's the challenge. How do you sample from this vine? Like, how do you generate realistic data that follows all these complex rules? Enter algorithm 4, a step-by-step process that starts by planting seeds with random values, then works its way up the vine. It uses a mathematical trick called the inverse Rosenblatt transform, which acts like a roadmap. At each level, it uses something called the H function to move from one variable to the next, making sure the relationships stay true. It's like following a recipe where each step builds on the last, without messing up the flavors. Now here's where it gets really clever. Even though the vine has lots of branches, the algorithm avoids redundant work. Instead of recalculating the same relationships over and over, it focuses on unique connections. The math behind this, it's roughly OD2, where D is the number of variables. Think of it like organizing a party. You don't need to reintroduce everyone to each other if they've already met, just focus on the new guests. But there's even more. Algorithm 5 takes efficiency to the next level by choosing the best order to sample variables. It uses a greedy approach, like picking the shortest path through a maze. At each step, it picks the next variable that minimizes future work, guided by a mathematical structure called a greedoid. This isn't just random guessing. It's a carefully designed system that ensures every choice leads to the best overall result. It's like planning a road trip. You pick the route that saves the most gas, not just the first exit you see. The payoff? These algorithms let us model anything from climate change patterns to financial market risks, all while keeping computations manageable. By combining the flexibility of Vine copulas with the speed of modern computing, we're unlocking new possibilities for AI to handle uncertainty in ways that were previously impossible. So the next time you see a machine making a decision, remember, behind the scenes, tools like Vine copulas are working hard to make sense of the chaos. And with innovations like the Vine computational graph, the future of AI is not just smarter, it's more reliable, more adaptable, and more human.